Okay, so current is moving charge. Charge can move through pretty much anything. There's no such thing as a perfect resistor. So if we've got some kind of material, then we define current as the amount of charge that flows past a certain point per unit time. Think of it like traffic. Remember, all of electrodynamics was developed in terms of fluid dynamics. They literally thought of fluids flowing. So current literally means the same thing it would for a river current. How much water flows by. You stand at a river and you measure how much water flows in front of you per unit time. So it's the amount of current per unit time. Technically, it's a derivative. It's a rate of change of charge in coulombs per unit time. So current I, which is not a vector, even though it does have direction, it does point in a direction. We'll talk later about assigning a vector to I. So I might have maybe a wire that looks like this. And I might say my current is flowing this way. So it's flowing, just like this. So I'll draw little arrows on there to show you which way the current is flowing. But current itself is just at this particular spot, how many charges are moving by per unit time. And then later we can stick an extra vector on top of that, but I itself is not a vector. It's measured in coulombs per second, which we call amps or amperes. So 1 amp is 1 coulomb per second, named after the physicist Ampere. Now, we know nowadays that it's negative charges that move around. Electrons are the ones that move. But back in the day, they didn't know that. Michael Faraday knew there were two different kinds of charges. Ben Franklin knew there were two different kinds of charges, and they arbitrarily called one kind positive and one kind negative. That's completely arbitrary. It was actually Ben Franklin that decided electrons. They didn't really call them electrons yet, but what we would call electrons, he's the one that decided they would be the negative ones because he thought they stood still and he thought the positive ones moved and he had it backwards. So it's really Ben Franklin's fault. Remember, the whole key to charge is there are two kinds. It literally wouldn't matter which ones we had called positive or negative, and we kind of screwed it up. Now we got to deal with these negatives all the time. So what we do in physics classes is we go, you know what? We're going to ignore all that. We're going to deal with what's called conventional current, which assumes that it's the positive charges that move. So for us, current is the direction in which the positive charges are moving. Forget about the fact that it's actually electrons moving in the opposite direction. It will play no role whatsoever. We don't ever have to worry about that in this class. If you ever take solid state physics, you'll have to worry about who's the one moving. For us, we don't care. Conventional current is the direction that the positive charges are moving. So in a real conductor, sure, you might have electrons flowing to the left. We're going to pretend that that's the same thing as positive charges moving to the right. Okay. Oh, here, we will need this later. This will not come in today. In about a week and a half, we're going to need this formula. So I just want to point to it so we can come back to it. One way you could physically measure current is figure out the concentration of charge particles you have in your material, some kind of charge density. times that charge, times the speed at which those charges are moving, times your cross-sectional area. This will give you, if you just look at the unit analysis, in here is charge per unit volume. Just look at the unit analysis, you get coulombs per second. Drift velocity here is kind of interesting. Let's talk about that for a minute. If I go over right now and I turn a light on in the room, so I'm in a room here, here's me, here's a light switch, up here on the ceiling is a light. I flip that switch, how quickly does that light come on? Just think about it for a second. If we were face to face, I would have you guys yell out answers. How fast do you think the signal travels from the switch to get that light switch to go on? It's very, very fast. It's almost the speed of light. It's not quite. It's about 180,000 meters per second, or miles per hour. Speed of light's 186,000 miles per hour. So it's almost the speed of light that the signal travels, that the electric field travels. How fast do you think the actual charges are moving here? Again, we know that it's actually negative charges that are moving. It's actually electrons that are moving. But let's just pretend that it's little positive charges that are moving up here. How fast do you think that happens? It's nowhere near that fast. In fact, you could walk faster than them. It's like 2 or 3 miles per hour. That's the drift velocity. That's how fast actual charges move through a wire. Because think about what a wire is. It's a whole bunch of atoms and molecules, right? And electrons are being freed up. This electric field is freeing electrons and knocking them off of atoms. We have a bunch of valence electrons, if we have a metal, that are easy to knock off their atoms. But those electrons then are bumping into another electron. They're bumping into another proton. They're kind of bumping all around. And they're very slowly making their way down this wire. So drift velocity is actually very slow. That guy right there. Okay, now this won't play a major role, but we will use J particularly when we get to Ampere's law. That's when J will become important. J is a vector, and it's the current density. It's current per cross-sectional area. So it's this guy we had up here without the A. So you got this wire here. You want to measure how much current flows across a cross-sectional area, say this circle right here. Charge or current per cross-sectional area, current density. So that's amps per meter squared, and it is a vector. And he'll be important when we get to magnetic fields and Ampere's law. But in this chapter, J doesn't really play much of a role. Resistivity is a measure of how good a particular material is at stopping current. So by definition, we call resistivity the electric field divided by the current density. So you apply an electric field in a material, you measure how much current will flow per unit area, cross-sectional area. So you have to apply, say you apply a really big field and you don't get much current, then you have a very resistive material. But if you apply a small field and you get a big current, then this would be very small. You would have a very non-resistive or conductive material. So resistivity is a measure of a material's ability to resist current. It's material dependent. It's not chunk of metal dependent. All copper in the entire universe has the same resistivity. This is depends on the material. Two different chunks of copper might have different resistances, but they have the same resistivity. Okay, if you take the reciprocal of that, you get what's called conductivity. Again, if you take solid state physics, you'll talk a lot about conductivity. We don't here. Okay, now resistivity is temperature dependent. So when I say all copper in the universe, that's say all copper at 20 degrees. If you increase the temperature, it becomes more resistive because things are bouncing around more, so those charges can't flow as easily. And I mean, if you're curious, here's what resistivity for a metal looks like. Here's the formula for it. So resistivity for a metal gets bigger and bigger as you increase the temperature. So I'm not saying all copper, all everywhere always has the same resistivity. I mean, if you get two different chunks of copper at the same temperature, then they'll have the same resistivity. And here's a little table you could see at. Oh, those are coefficient. Yeah, we don't need that. Okay. If you're curious, semiconductors go the opposite way. If you increase the temperature, they become less resistive. This is why your computer works. If it weren't for this, we wouldn't be able to build computers that can fit on a table. Remember, they used to have to use vacuum tubes. That was until somebody invented the superconductor or the semiconductors. Superconductors are the opposite end of that. Superconductors have absolutely no resistance. This is not some theoretical limit. This is not like a math game we play. You know, a lot of times in math classes, you just pretend, or in a physics class, you approximate a chicken as a sphere, the whole spherical chicken thing. This is not an approximation. Superconductors are real materials. You can buy them. And below some critical temperature, you literally get infinite conductivity, zero resistivity. Charge flows for absolutely nothing. It's completely free. Superconductor. I got a warning, my internet connection is unstable. Can you guys hear me? Am I cutting out? You can hear me? Okay. So everybody that's working in that field is trying to develop what we call high temperature superconductors. And by high temperature, I mean like negative 100 degrees would be considered high temperature. I don't mean 1,000 degrees. That's never going to happen. If we could find a room temperature superconductor, that would revolutionize all of physics. It would change all of technology if we could find room temperature superconductors. I think the best we found is on the order of like negative 50 degrees Celsius when they transition from superconducting to non-superconducting. Okay. After resistivity, we get what's called resistance. This is chunk of stuff dependent. You have something in your hand. That thing you have in your hand has a certain resistance. That material all has the same resistivity, but the one in your hand has a specific resistance. So resistance R is rho L over